Hi, everyone. In this lecture, we're going to start talking about the subject of differential geometry. Now, for some people, getting to talk about a new area of math will be innately interesting. But I think that there is a real question that others may have, which is why do we need more abstract math in this course? And the answer is that it serves us a very important purpose. So, what is differential geometry? Well, in a word, differential geometry is the geometry of smooth surfaces and shapes. So, for instance, it tells us how to work with objects like a sphere or a torus. And that's all very helpful in general, but that's actually not what we need in this course. Here, we're more interested in another aspect of differential geometry, which is the ability to work on these kinds of surfaces or any kinds of surfaces in a way that does not depend on the particular coordinates that we choose. Or, maybe to state it another way to switch between coordinate systems on a space. Uh, OneNote is misbehaving again. Okay, why would we be interested in working with different coordinate systems? Well, thus far, we've always described our state space in terms of internal energy work coordinates. But going around in the real world, if I asked you to go and get me a box of gas at standard temperature and pressure, such that the volume of that box was 1 liter, you wouldn't bat an eye. That is a complete description of the state of that system in terms of thermodynamic coordinates. Or similarly, if I asked you to get me a gas with a certain number of atoms or a certain mass at a certain temperature in a certain volume, that would also seem sufficient. So, in other words, there are ways to specify the thermodynamic state of a system that do not rely on internal energy and work coordinates. Okay, I'm going to take a minute and fix this OneNote issue, and I'll be back in just a sec. Okay, welcome back. Now, the central object of differential geometry is called a manifold. I'm not going to define this concept too carefully, but roughly speaking, a manifold, in particular, we're interested in smooth manifolds here, is a shape in some number of dimensions, which can be sort of related smoothly to Rn. So it will be, it for us, in fact, just a certain subset of Rn. And I'll say well behaved here to indicate that whatever subset we pick can't be too badly behaved at the boundaries. Okay, another part of being well behaved is that this subspace should still be n dimensional. In other words, at every point, we need n coordinates to specify the point in question. So it's n dimensional points are specified by n coordinates. Now, what's true about coordinates? Well, whatever coordinate system we pick, if it is a so-called good coordinate system, then every point will be distinctly specified by n points, by a certain value of the coordinates. So let's make that a little bit more formal. So for good coordinates, every set of coordinates corresponds to a point on the manifold. Okay, let's give an example. So for the ideal gas, the manifold is the state space gamma. And in fact, I'll usually just use gamma here. Gamma can be specified by UVN coordinates for the ideal gas. And um, in particular, where U is between 0 and infinity, or maybe we'll just say U greater than 0, V greater than 0, and N greater than 0. In other words, here gamma is equal to the positive octant of R3. And these three coordinates are good coordinates in that every point in the positive octant of R3 corresponds to some specific set of values u, v, and n, and every set of coordinates u, v, n corresponds to a point on the manifold. Now, what would be a bad coordinate system for the ideal gas? Well, for instance, T, let's in fact do a different order, UTN. And why is that? Well, U is equal to 3 halves N KBT. So consider the 2 points in UVN space given by, let's say, 1 joule, just to make things a little bit specific, 1 liter, and 10, let's say 10 to the 7 particles. Why not? And compare that to 1 joule, 2 liters, 10 to the 7 particles. Now, these are clearly distinct points, or these coordinates represent distinct points on gamma. But let's look at their UTN coordinates. So U for this is 1 joule, but T is equal to, well, it's 3 halves times 10 to the 7 times KB. Oh, I'm sorry. U is equal to this, so 1 joule is equal to 3 halves times 10 to the 7 times KB times T. And here we have 1 joule is equal to 3 halves times 10 to the 7 times KB times T. So in other words, these two systems have the same temperature. But, so in other words, their UTN coordinates would be the same, but they represent different points. And that means that UTN must be a bad coordinate system. All right, so with that out of the way, let's now talk a little bit more about manifolds and coordinate systems. For that, we're going to need to draw a picture. So let's draw a picture of some arbitrary abstract state space. So this will be the space gamma. And we want to draw a picture of the coordinates. So what I'm drawing now are going to be level sets in a coordinate system. Let's say that this coordinate system is A1, A2. Okay, so these are the level sets for A1. So this will be A1 is equal to, let's say, -3. Here's A1 equals -2. A1 equals -1. A1 equals 0. A1 equals 1. A1 equals 2. A1 equals 3. A1 equals 4. And A1 equals 5. And now let's do the same thing for A2. Oops. So this can be A2 is equal to -2, A2 equals -1, A2 equals 0, A2 equals 1. Okay, and so these are good coordinates. This is a good coordinate system in that these lines are never parallel at any point. That would make it a bad coordinate system. This will be a little bit clearer if we spend a second talking about vectors. So we will come back to that image. Okay, so what is a vector? You probably learned in high school that a vector is an object with magnitude and direction, but without position. So your teacher may have told you something like this vector and this vector, which have the same magnitude and direction, should be considered equal. Good. Now in differential geometry, this last point is not true. Instead, we're going to consider every point on the manifold having a sort of identical copy of a vector space glued to it. So on state space gamma, we will consider there to be a copy of Rn at each point x, denoted T sub x of gamma, called the tangent space at x. Okay, that's not very good. There we go. Okay, so now let's look at what that looks like. So if this is the point x, let's choose a good point. How about right here? Then we consider that we can come up with vectors at this point. So let me draw one. And that vector would be different than the vector here in the sense that they don't live in the same vector space. If this is the point x and this is the point y, then this vector, let's call it capital V, lives in the tangent space at x, and this vector, let's call it w, lives in the tangent space at y. Okay, good. Now I'm going to erase this because we need to talk a little bit more about these vector spaces, about these tangent spaces. Every vector space in finite dimensions has a basis, and we'd like to figure out what a good basis for this is. Now, maybe you can already kind of see a way that we could choose a basis. We have these lines, the red lines and blue lines, that are telling us something about the coordinates on this manifold. And so what we want to do is use those in order to specify a basis. So here's what we'll say. We have a distinguished basis for t sub x of gamma given coordinates a1, a2, denoted by partial a1, partial a2. Now, for the time being, we're using these partial derivative symbols, but they just mean these basis elements. We're not using them to denote actual partial derivatives at this point in time. But I should be able to tell you about their magnitude and direction. Now, the direction is very easy to tell you about. And we want to use the inspiration of thinking about partial derivatives here. So the partial derivative, partial a1, is going to be something that points in the direction that increases a1 while keeping a2 fixed. In other words, it points along this line. And similarly, partial a2 should point in a direction that keeps a1 fixed and increases a2. So in this case, I'm actually going to move this x a little bit. In this case, it points down because a2 is increasing as we move down the page. Good. Now, in terms of their magnitude, the magnitude is going to be dependent on how close together these level curves are. In other words, how quickly a1 or a2 is increasing. We won't get into that too much here, but it at least gives you a picture of how we would determine this. And now that we have a basis, well, we're basically good. We could write v in this basis. V is some vector here, and we'd like to figure out what its components are. So let's figure that out. Well, we typically write them in this way. So for the time being, this is all we need to know. We have some vector and we can write its components in this way. I do want to note one thing here, which is that notice that a1 appears twice in this term and a2 appears twice in this term. It's probably a good time at this point to introduce the so-called Einstein summation notation, in which if an index is repeated twice, once as a superscript and once as a subscript, then we sum over it. So we could also write this equation or this expression that I've written to the left as v upper aj lower partial aj, or partial lower aj. So notice that here, this is a superscript, and here it's a subscript. This is just notational convention, and we will use it at some points. I'm going to give us a little bit more space, and then we'll hop back into the video. Okay, the next concept to bring up is the concept of a vector field. And this would be a set of maps from each point in gamma to, let's say each point x in gamma to tx gamma. So in other words, it's a set of maps that, oh man, what is going on here? Interesting. It's a set of maps that glue a vector to every point on the manifold. These will become important as we continue to study things, and I just wanted to bring them up. We have one last thing to talk about in terms of vectors, which is the fact that vectors have a natural action on functions. Now, for those of you who have taken vector calc, you actually have already seen this before. It's the directional derivative notion. And let's review what that means. Suppose that we have some function. So here's a function on a two-dimensional space. Let me draw let's try again. Here's a two-dimensional space. And there's a function on that space that's going up and down and so on. And imagine now that we have a vector. Say this is the vector little v. The directional derivative would ask us how the function changes as we move in the direction of little v. It's typically written like this. Oh, and let me use a vector hat. We don't typically use vector hats in differential geometry, but for the time being, let me use them. We would typically write the directional derivative in this way if this was the function f. So v dot del acting on f. And we could write that out in coordinates as well. We would get, if we had xy coordinates here, we would get vx times partial x plus vy times partial y acting on f. Good. Okay, so how do we generalize that here? Well, if we have a vector field, or in fact, we don't even need a vector field. We can act on a function and just get the directional derivative at this point. So if we have a vector v, which is Vaj, partial aj, then we can allow it to act on f that takes gamma to the reals by v acting on f, and we'll put that action in square brackets, is equal to Vaj partial ajf. And now this means an actual partial derivative. So whereas before we were simply using partial derivative notation in order to sort of write these basis vectors, now we're actually using them for vectors. And this sort of justifies the notation. When we have the vector act on a function to perform the directional derivative, we're actually going to use those partial derivative basis vectors in order to act on the function. And that concludes everything that I have to talk about vectors. So in the next video, we'll look a little bit more closely at coordinate transformations and how we can use them to do some problems. All right, I'll see you in the next one. Thanks for watching.